So let us start. So in our last class, we studied parallel plate transmission line, as you can see here, and we solved number of equations, and finally we got capacitance, inductance, and the loss terms for this transmission line. So the thing is, this is one of the very conventional transmission line. Particularly, I'm talking about parallel plate transmission lines. So just a minute. The students are still joining. Yes. So we fixed in the last class that C, L, R, and G. So these values actually, the expression for C, L, R, and G, we derived in our last class for parallel plate transmission line system. Correct? Now the thing is, as I told you, in a daily life, we came across different kind of transmission lines. Like I shown you in our first class that coaxial lines are there, two-wire lines are there. So these are the different kind of transmission line, and one of very important thing you studied in electromagnetic, which is a waveguide. This is also a kind of transmission line. So what we will do today, we'll try to derive these parameters, transmission line parameters, which is C, L, R, G, for different, rather I should tell, having the same physics those transmission line having, like parallel plates, two-wire, and the coaxial line. So that is why I wrote here the journal transmission lines. So we are going to talk about the two conductor system mainly, and this includes first parallel plate, second two wires, and third is the coaxial lines. Fine. So for these transmission lines, two conductor systems, will try to derive the parameters C, L, R, and G. Correct? Now the thing is, if you see these transmission lines, so there is a common thing is that there are two-wire system or parallel plate system. Correct? And the thing is, like, we can express the transmission line parameter in terms of the lump parameters. Correct? We have seen in a last class. So let us take a transmission line. So I'm drawing here a two-wire transmission line. Correct? And this is infinity long. Let us consider this is a infinity long. Now the thing is, as we know that throughout the line of the transmission line, the material parameters and other things will remain same. So what we will do, we'll take it out a small segment of this transmission line as delta Z. If this is a Z direction, so let us take a differential length is called as a delta Z. Now, so in the previous class we have seen that two conductor system or parallel plate system we can express in lumped system. So let us make the equivalent circuit of this. So first time I'll draw, then I'll explain. So this is a resistance, then we have an inductor, and in a shunt we have dielectric losses, and we have the capacitance. Right? And let us define some of the parameters here. So this is R delta Z, this is L delta Z, this is C delta Z. I'm multiplying with delta Z because these capacitance, inductor, and all the things are like Henry per meter, Farad per meter, like that. Because we have to accommodate whole transmission line, and we are particularly talking about the segment of the transmission line. So let's make it per meter kind of thing, so that when we'll multiply with the required length, so we'll get the total capacitance or inductance, and G delta V. Right? No. So once we have the circuit actually, so it is better to mark the voltages and current. I would say here the voltage voltage wave and the current waves. This would be better thing because we are dealing with the electromagnetics. Then we converted the things in a lump model. So definitely you can say voltage and current, but voltage wave and voltage current and current wave, I think more justified. So let us define here the terminal voltage waves as like this. This is V, the function of ZT at this terminal, and at output side this would be V is a function of Z plus delta Z comma T. Why? Because we taken here a differential length of transmission line, which is delta Z. What is V? V is the instantaneous voltage. V is the instantaneous voltage, and these parameters are here ohm per meter, Siemens per meter. These are the losses, different losses, and L inductance is what? Henry per meter, and capacitance is Farad per meter. Like for this differential length, if we are defining these capacitance, inductance, and losses per unit length, so it is quite clear that when we are talking about, let's say, 1 meter cable or 2 meter cable, or let's say 100 meter cable, so we can accommodate, we can say, okay, this is the total capacitance offered by this cable or capacitance. Right? So the thing is, the next question should come in our mind, that why we arrange in such a manner. Fine. So like you can see here, the inductor is actually in a series and capacitor in shunt. Fine. Now, if you talk about the losses, so the ohmic losses we kept in a series, whereas the dielectric losses in a shunt. It is quite clear that, let's say, if you have the two-wire system, so in between there must be dielectric or maybe the air. Fine. So there must be some capacitance between these two wires or plates. So it should be in shunt. Similarly, the losses offered by the dielectric we supposed to put in a shunt, because mainly we are dealing with the shunt elements here. Now, if you talk about the series elements, so along the wire, when the current will flow, it will experience the resistance, and this resistance is nothing but offered by this metallic wire, ohmic losses. So better to put in series, fine. And as I told you, at very high frequencies, when the lambda is very small, so this wire will contain a flux, and hence we have inductance. So this is a justification why we kept all these elements in series and shunt arm. Now after having the circuit and the voltage and current elements, it is quite easy uh, for us that we can apply the simple uh, rules what we learn in network theory. Fine. So let us assume this is the current here, I z comma t, and at this side the current is I z plus delta z t. Fine. So now we have all the current, voltages, all the things over this circuit. Now let us solve the circuit. Forget about all the electromagnetics and all the things. Now we have a simple circuit here, and we can solve very easily these things. So how we will do? We simply apply KVL, KCL, and all sort of things, and we can manage the things. Correct. So what we need to do, that we supposed to apply the KVL and then KCL at this node N. So let us apply the KVL here. So if you apply the KVL, so what you can write from this circuit, please check. V is a function of z comma t minus, the students are still coming and it is difficult for me because all the time on the screen I'm getting the requests. So please join on a time. So V z comma t, this voltage, then drop across here. So we can write R delta z and the current flowing across this, which is I z comma t. Fine. Then minus L delta z dou I, which is a function of z comma t, divided by dou t, minus V z plus delta z comma t is equal 0. Fine. So easily one can apply the KVL and simply one can write this equation. So Vz, this particular thing, fine, then drop across here, drop across here, and ultimately the voltage at the output side. Fine. So we accommodated all the things in this equation. Fine. Now what we need to do further, we need to rearrange. We need to rearrange this equation, and if you rearrange, I'll write some of the intermediate term and then we'll see. So when you rearrange, so what this equation will look like, this will be V z plus delta z comma t minus V z comma t divided by delta z is equal to Ri z comma t plus L dou I over dou t. Fine. Yes, we can do. There's no issue with this. So now the thing is, if you see this equation carefully, so we can convert in a partial, this particular left hand side we can convert in the partial differentiation, and this is what the definition is actually. And so finally one can write these things as for delta t if tending to 0, so you can accommodate like this: dou v is a function of z comma t over dou z is equal to Ri z comma t. Like this current and voltage here is a function of space and time, but the thing is, like we need to separate it out. We cannot solve like this. So later we'll see that how we can separate these things. L dou I z comma t dou t. So this is the equation. This is one of the equation. Fine. So this is, let's say, equation number 1. Fine. Now what we do next? What we do next actually? So what we have seen so far, we have a circuit, and this is the equation when we apply the KVL. In the same way, you can apply the KCL at node N. This node, you can see this node N. So we can apply the KCL here, and when you apply the KCL and taking these things delta z tending to 0, so you can write another equation in the same way. Like I should write the equation. So this will be I z comma t minus g delta z into v z plus delta z comma t minus c delta z dou v over dou t. But this would be the function of z plus delta z comma t divided by dou t minus I z plus delta z comma t is equal to 0. Fine. So this is what the KCL actually. If you check at node number N. Now the similarly we'll do rearrange the equations, and if you rearrange the things, so you can write a very good equation, a similar kind of equations actually, not good, a similar kind of equation. I z comma t divided by dou z z g v the function of z comma t plus c dou v z comma t divided by dou t. So this is another equation, correct? Now right now we have two equations, equation number 1 and equation number 2, coming from KVL and one from KCL. So these two equations, equation number 1 and equation number 2, we called as journal transmission line equation. Transmission line equation. TL stand for transmission line. Or in some places, in some books, correct, This is also defined as the telegraphist equation. What is that? Telegraphist equation. So you please remember these terms, correct? So these are the two equations, and this is the general transmission equation. And now the story is complete here. Why? Because once you have the equation, you can do some further things to get the output parameters to relate some of the equations, correct? So this is the thing. Now, as I told you, we accommodated here the space and time like that. Like as an engineer, correct, electronics engineer particularly, it is difficult to deal time and space if clubbed like this. We cannot do. So there must be some assumptions. There must be some things we need to incorporate here so that we can separate out space and time. Correct. However, this is illogical when I say that we are going to separate time and space. But within some limitations we can do. So as an electronics engineer, we are aware actually the phasor forms, correct, or time harmonic equations, if you remember from your electromagnetic course. So let us write down here those things, and then we'll recall these two equations, about two equations, and we'll solve. So what we'll do, we'll use the phasor forms, correct? And if you write the v is a function of z comma t in a phasor form, how it will look like? This will be the real part of v, the function of z means only the space. You can see here v is a function of space z, xy, maybe xyz also. We are going this thing 3D geometry into e to the power j omega t. Yeah? And I as like this. I believe you know these things, phasor form and all. Fine. So here this is the space and this is the time. Periodic time. So periodic nature we are accommodated here with the space. Now what we will do next? We need to recall the above two equations. What they are? The first equation is this. So just a minute. So this is one equation, and another equation is this one. So let us copy this equation. Like this time I'm missing the blackboard so that I can immediately write the things, but here I'm learning that how to deal these things, correct? So now we have two equations, correct? I manage somehow. Fine. So these two equations, what we will do, we'll put this time harmonic form or the phasor form in these two equations. Now if you do this, so you can rewrite these two equations as time harmonic transmission line equation like this: minus d Vz over dz is equal to r plus j omega l Iz and minus d I is a function of z dz g plus j omega c vz. Fine. So this is what? This is your time harmonic transmission line equation. Fine. Now the thing is, we can play with this equation and we can find it out number of things. So if, let's say, the lossless condition, because initially we'll start with the lossless case. So R is equal to 0 and G is equal to 0. So you can rewrite the equation, and this would be the transmission line equation for lossless system. Right? So this is the thing. So particularly these transmission line equations are very important. And what is next actually? The thing is, we need to find it out. Solutions. What solution? Because if you see, these are coupled equations. If you see, these are the coupled equations. Fine. Okay. These are the coupled equation. Why coupled equation? Because in both the equation, the V and I are related. Please check. V and I are related. Now what we need to do? We need to decouple it. How you will do these things? You need to again differentiate with respect to z. Any of your equation. If you redifferentiate with respect to z, so you can decouple it. Why? Because when you do the differentiation with respect to z, so this become di over dz, and this term could be recall, and you can put there. So the whole equation in terms of v. Or similarly, if you differentiate this equation number second, so again you can do like this. So in this way, you can what you can manage actually, you can do a very nice equation, which we are also did actually in electromagnetics. And if you remember, if you redifferentiate this thing, so this will be first and this is second. If you remember, we also perform these things in a parallel plate system also. Remember these things? What is gamma? Gamma is a propagation constant. Fine. What is gamma? Gamma is propagation constant. Alpha plus j beta, or under root r plus j omega l g plus j omega c. This is propagation constant, and unit is per meter. Fine. So what we have, what we seen today actually, we tried to have the equivalent circuit of the transmission line, journal transmission line. Then after we wrote the transmission line equations with the help of the applying KVL and KCL. Then after we used the Phasor forms, fine, and we converted these journal transmission line equations in time harmonic transmission line equation. And then after, what we did, we redifferentiate these equations, and this is now the second order differential equations, and this form we manage. Now this is the second order differential equation, and this second order differential equation we supposed to solve it. So as I told you in a last class also, for parallel plate transmission and how we selected the solution. Now the thing is, I'll ask to the students, you please check the book and please have a look over the solutions, that why they written a particular form. I'll not write here. I'll suggest you please go through the book and find it out, these things, and please check, please read it about the solutions, why they're taken, and with this solution what we can do. Fine. So today we'll do this much, and next class we'll start that the solutions of the second order differential equation, and we'll try to learn about the physics, why these solutions we chosen, and we'll see some of the special cases like lossless lines, correct, and distortionless line. These things will study, and finally we'll see some of the transmission line parameters again in terms of the geometrical parameters of different two-wire system. So this is all about. Okay, so if you have any questions, you can ask.